Today, we're diving into something pretty amazing, a story of transformation. We're going to see how a really common agricultural waste product is secretly making our buildings stronger and, believe it or not, our planet a little bit greener. It's a great question, right? On the one hand, you've got rice husks, the flaky shells left over from milling rice. And on the other, you've got these massive concrete structures, the very foundation of our modern world. How on earth could these two things possibly be connected? Well, the secret is in the ash. When you burn those rice husks under just the right conditions, they create this incredible material called rice husk ash, or RHA for short. And it turns out this humble ash has two really powerful ways of upgrading concrete from the inside out. Okay, so first up, let's talk about the chemistry. To really understand how RHA works its magic, we have to zoom way, way down to the molecular level, where it performs some pretty cool tricks inside the concrete mix. You see, when cement mixes with water to harden, that's a process called hydration. It creates this super strong binding gel that holds everything together. But it also produces a weak link, a byproduct called calcium hydroxide. This stuff doesn't really add much strength, and worse, it's vulnerable to chemical attacks. And this is where our hero, RHA, steps in. It is packed with a special, highly reactive form of silica. This silica actively seeks out that weak calcium hydroxide and triggers a reaction that actually creates more of the good stuff, that strong, durable binding gel known as calcium silicate hydrate, or CSH. So you see, RHA isn't just a passive filler, it's an active participant in the concrete's chemistry. It literally takes a vulnerability, that calcium hydroxide, and upcycles it into the very compound that gives concrete its strength. Pretty clever. And this whole process has a name. It's called the pozzolanic reaction. This is the core chemical reason why adding this simple ash makes concrete fundamentally better, more durable, and way more resistant to chemical damage over its entire lifetime. But hold on, the chemistry is only half the story. RHA doesn't just work on a molecular level, it also physically reinforces the concrete. So let's take a look at what we call the filler effect. So, if you could shrink down and walk around inside a block of standard concrete, you'd see it's not a perfectly solid mass. It's actually a matrix filled with these tiny, microscopic pores and voids. Think of them like little highways for water and harmful chemicals to seep in, which over time can lead to corrosion and all sorts of damage. Now, the particles of rice husk ash are incredibly fine, way finer than even cement particles. So as they get mixed in, they act like a microfiller. They physically get into all those little gaps and plug them up, which makes the whole internal structure much, much denser and more compact. And the end result is a fundamental shift in the material's properties. You go from a porous, permeable structure to one that is super dense and practically watertight. This is absolutely crucial for long-term durability because it helps prevent things like freeze-thaw damage and protects the steel rebar inside from rusting. So we have a chemical upgrade and a physical reinforcement working together. Now that we understand how it works, let's look at the real-world proof. What does this actually mean for the final product? So you've got this powerful 1-2 punch. The chemical reaction creates more of that strength-giving glue, while the physical filler effect makes the entire structure tougher. And when they work together, the result is pretty impressive. Let's look at a specific case study to see this in action. Some researchers in Bangladesh created a concrete mix where they replaced 15% of the regular cement with rice husk ash. Then they tested it against a normal control batch. So what was the first major finding? After 28 days of curing, the RHA-enhanced concrete showed an 8.5% increase in compressive strength. It was quantifiably, measurably stronger. And hey, remember that filler effect we were just talking about? Here's the proof. Water absorption in the RHA concrete dropped by a massive 23%. That is a much denser, less permeable concrete, which is exactly what you want for long-term durability. Looking at these numbers on a chart makes the difference really plain to see. The standard concrete topped out at about 35 megapascals of strength, but by replacing just 15% of the cement with RHA, that number jumped to 38 megapascals. That's a clear, significant improvement from adding what is, let's be honest, agricultural waste. So the concrete is stronger and more durable. That's fantastic. But the benefits of RHA go far beyond just material science. There's a much bigger story here, and it's all about sustainability. And this is where the story gets even bigger. Every ton of RHA we use is a ton of waste that isn't going into a landfill. It also means we need to produce less cement. And let's not forget, cement production is a major source of global CO2 emissions. It's just a perfect example of a circular economy, turning one industry's waste into a valuable resource for another. And that leaves us with a pretty fascinating final thought. The story of rice husk ash is a powerful reminder that the solutions to some of our biggest engineering and environmental challenges might just be hiding in plain sight, in the very things we currently throw away. The only question is, where are we going to find the next one?